the last section in chapter 15, 15.2. We've been talking about waves, we've been talking about sound. What's one of the ways in which you hear lots of sound? Music. Now, I will be the first to admit that I am the least musically inclined person in the entire Hayfield School District. I am awful at music, singing, playing instruments, everything. But the physics part of it will make some sense. So we'll counteract. So where are some sources of music? Think about your instruments. Where do sound come from? There's a wide variety of places where sound comes from. You have your voice, which is vocal cords, all the way down through all different types of instruments. Your brass instruments, trumpets, trombones, everything, reed instruments, flutes and pipe organs that have open pipes, and your string instruments, your guitars, your harps, things like that. All of those are capable of producing sound. Now, when we talk about sound, what we're going to talk about a little bit is resonance, particularly when we are talking about flutes and pipe organs. Resonance can occur. Now, what is resonance? Well, let's say, for example, here is a tube with open on one end at the top. And what happens is my sound wave travels down, just like that. What's going to happen is there could be another wave that entered or another wave that's coming back that's like that. And you have matching waves, all right, that pretty much cancel each other out. That is resonance. So resonance is really when I have two waves that kind of counteract one another, a resonating pipe at one end. So I could have a tube open at one end with water on the bottom, hit it, and this wave can go, and I might have another wave coming from the same origin at the top that's in resonance. So that would be how resonance in an air column works. When we talk about resonance, you can cause resonance from a standing pressure wave. For example, if I hold a tube over water, the tube, the end that's in the water is my closed end. Obviously, the other end is my open end, and I can create resonance that way. You can measure wavelength with resonance, all sorts of things. You're going to have a couple math examples dealing with resonance. And remember, really, that two nodes, right here, two nodes or antinodes are separated by half a wavelength. So if it tells you how many nodes are in a wave, you can draw the wave. Two nodes is half a wavelength. Just kind of picture that. It's kind of the up. And if it goes to the third node, that would be the down. So kind of, we'll talk about that in class when we have a question like that tomorrow. Continuing with sound quality. Sound spectrums. We have things called fundamentals and harmonics. What are fundamentals and harmonics from a physics standpoint when we're talking about music? Fundamentals is the lowest frequency of an instrument, and harmonics is the odd number of multiples of the fundamental frequency. So kind of the range of sound that that instrument can make is harmonics. When we talk about consonance and dissonance, just really two key vocabulary words, which means a pleasant sound of pitches or an unpleasant sound of pitches. We travel all over the HVL and see different pep bands. Some have consonants and some have dissonance. Now, that is dependent upon the ear. What you find pleasant, someone may find unpleasant. But consonance is just a pleasant sound of pitches, dissonance an unpleasant sound of pitches. Musical intervals. You probably hear the word octave a lot in music or in band or in choir. What is an octave? When two note frequencies are related by a ratio of 1 to 2. Well, what's that mean? Well, let's say, for example, I have one tuning fork with a frequency of 440 hertz. My second tuning fork has a frequency of 880 hertz. That, since it's a 1 to 2 ratio, the second one is essentially doubled of the first one. The 880 hertz tuning fork is 1 octave higher than the 440. So when it's a 1 to 2 ratio, it's 1 octave higher. If it was 1 to 3, it would be 2 octaves higher. Last thing when we talk about music, and then we're wrapping up chapter 15, beats. Oomps, 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 oomps. Beats. What is a beat from a physics standpoint? It's an oscillation of a wave amplitude. The frequency of the beats equals to a change in frequency. So what you're going to have is you're going to have two different waves. You're going to want to solve for the frequency of both those waves. If the change in those frequencies is equal to the frequency of the beat. So bazoom all right, I just had like two different beats going on there. The sounds I were making were at two different frequencies. So you pick that up as a beat. Now, if the change in those frequencies is less than 7 hertz, you're going to notice that as sound and not a beat. More than 7 hertz, you're going to recognize that as a beat. So this is kind of the one equation that we have for sound. The change in frequency is equal to the frequency of the beats. But that's sound. That is music of sound. Very short section, but important things there when we talk about sound. You will have a test on Chapter 14 and Chapter 15 combined very shortly.